Hello everyone. Today, we are presenting the results of our capstone project. The topic is, From Data to Insight, University and College Admission Analysis Combining TrueSKill and LLM. Our presentation will be divided into 7 parts: abstract, research motivation, research objectives, research framework, research methodology, website demonstration, and conclusion and future work. First, we utilize the ranking mechanism of the TrueSKill algorithm, which offers dynamic evaluation, competitive learning, and scalability. The experimental results are then summarized using an LLM, large language model. Part 2. Research motivation. In recent years, due to Taiwan's declining birth rate, the number of students has been dropping year by year, and the competition for student enrollment among universities has become increasingly fierce. We observe that when formulating admission strategies, most schools still rely on subjective evaluations such as word of mouth or social impression, lacking objective analysis based on data. This situation leads to a phenomenon where the strong remain strong and the weak remain weak. Schools with good reputations easily attract students, while others struggle to gain visibility even with effort. Therefore, we hope to establish a more objective, quantifiable, and dynamically updated system for analyzing school competitiveness through data analysis and artificial intelligence technology, helping educational decision-makers and students gain a clearer understanding of the actual gap between schools. Part 3. Research objectives. The main objective of this project is to introduce the TrueSKill ranking mechanism and apply it to the education sector to simulate the competitive process and the strength disparity among various schools in the admissions market. TrueSKill was originally a multiplayer competitive rating system developed by Microsoft, which estimates the relative ability of each participant through match results. By applying this algorithm to education, we treat each school's admission result as a series of competitive matches. Through this algorithm, we calculate each school's average strength value, mean, $/mu$, and uncertainty, standard deviation, $/sigma$, thereby establishing a school competitiveness ranking mechanism that is both fair and updatable. Part 4. Research framework. Our project framework is divided into 4 stages. 1. Data collection. We collected the data for the technological and vocational college entrance selection and distribution admissions from 2022, year 111 of the ROC calendar, to 2024, year 113, including the number of admitted students, minimum scores, preference order, and application status. 2. Data preprocessing, data cleaning and field standardization. 3. Data calculation. We use the TrueSKill algorithm to calculate the relative ability of each school/department/group, and then use the collected data to calculate and define various metrics. 4. Large language model application. Finally, the TrueSKill data and other metrics are fed into the LLM, which automatically generates a textual analysis and suggestions for each school, such as which clusters have improved performance and which need improvement. Part 5. Research methodology. This section primarily explains how we apply TrueSKill to the competitive analysis between school departments. We treat each school/department/group as a player, and the candidate's preference submission is treated like a competition. When a candidate is admitted and ultimately chooses a specific school department, we can determine which department won the match based on this result. Through a large volume of such match records, TrueSKill automatically calculates the relative strength of each school department, which we call the R_score. This score is more dynamic than simply looking at the admission scores, as it reflects the school's true popularity and competitiveness in the eyes of the candidates. As illustrated in this figure, if a candidate is qualified for programs A, B, and C simultaneously and is finally admitted to Program A, then in the matches of Program A versus Program B and Program A versus Program C, Program A is the winner. In the match of Program B versus Program C, neither side is the winner, so it is determined as a draw. Next, we introduce several data indicators designed in this project. First, for the entrance selection channel. Enrolled effectiveness represents the percentage of successful applicants who actually register. A higher number indicates stronger attraction to students and a more successful admission strategy. Quota vacancy rate, used to see if the enrollment quota is filled. A high vacancy rate may indicate insufficient attraction for that department in the given year. Admission rate, the ratio of actual admitted students to applicants. This reflects the department's efficiency in achieving its enrollment goal through the selection channel. Transfer ratio of quotas to distribution represents the percentage of unfilled selection quotas that flow to the subsequent distribution channel. A higher ratio may indicate weaker competitiveness in the selection stage, impacting the overall admission strategy. Next, the distribution admission indicator. We use the average score for distribution admission to observe the department's performance in the distribution stage and compare it with the TrueSKill R_score to see if the actual competitiveness aligns with the candidate's score trend. Finally, the TrueSKill core indicator, R_score. This score is the relative strength score, dynamically calculated by our model, which more accurately reflects the department's popularity and true competitiveness in the students' minds. This page primarily explains how we utilize the large language model in our research. We deployed the Gemma 3 model locally using Alma. The advantage of this approach is that it enhances data processing speed while ensuring data privacy and security. In terms of usage, we are not retraining the model but using prompting, designing structured textual instructions to guide the model to perform analysis on the data. The entire analysis process is divided into 3 major tasks. Data summarization and anomaly identification helps quickly find characteristics and issues in the data. Indicator linkage analysis compares the relationship between the R_score and other indicators. Conclusion generation, the model integrates the analysis to automatically generate reports. Through this integration, we transform the original cold data into semantic information, making it easier to understand the analysis results. Next, we demonstrate the complete technical integration flow of this project. I will introduce it in a few main parts: front-end, back-end and database, AI analysis, and the containerization management of the entire architecture. First, let's look at the front-end, web page, and back-end, API. The front-end uses familiar HTML, CSS, and JavaScript to build the web interface. This is where users interact and see the results, and its main responsibility is to present all data and analysis results. When a user operates on the front end, it connects to the back end via API. The back end is the core logic of our application. It receives data from the front end in JSON format. Concurrently, the back end is responsible for interacting with our database, PostgreSQL, to perform the task of storing historical data. Next is our core component, the AI analysis flow. After processing the data, the backend transmits the necessary data for the current analysis to our AI analysis module. The AI analysis module runs on the Alma language framework, which is responsible for hosting our selected large language model, LLM, which is Gemma 3. Gemma 3 will generate the response content based on the analysis methods, necessary prompts, and required analysis data. After the analysis is complete, the AI analysis module returns the AI analysis results to the backend, which is finally sent back to the front-end web page, allowing the user to see the presentation of all data and analysis results. Finally, the foundation of the entire architecture, containerization management, Docker. As you can see, our database, backend, and AI analysis module all run within a Docker internal environment. We use the Docker containerization management tool to package the entire application into one or more containers. This approach has 2 major benefits. Environment consistency, ensuring the development, testing, and deployment environments are identical. Deployment flexibility and efficiency, making the deployment, scaling, and management of the entire system very fast and easy. Part 6, Website Demonstration. First, after connecting to our website, you will see buttons on the top left to select the year and mode. Here, we first select the year 2022, 111 ROC calendar, department group as an example, type Hubei University of Science and Technology in the search box, and select the Department of Information Management below. The selected school, department, and category will be displayed on the right. Below, charts will be presented with explanations of their relevant meanings. You can also click on each chart to enlarge it for detailed viewing. Next, a social network graph will be presented, where the arrows represent the flow of students, which allows for a better observation of the competitive situation corresponding to the selected school. The very bottom section uses the LLM to consolidate and analyze the data for that department and summarize relevant issues or suggestions. Furthermore, we can click the Comparison of Changes button on the left. We again select the Department of Information Management at Hubei University of Science and Technology. On the right, we can choose the years. We will use year 2022, 111, and year 2023, 112, as examples. A red minus sign next to a school change on the right indicates that the Department of Information Management at Hubei University of Science and Technology was in competition with that department in year 2022, 111. A green plus sign indicates the opposite, and white means they were in competition with that department in both years. Part 7. Conclusion and future work. Through this research, we have successfully combined statistical models and artificial intelligence to establish an objective and dynamically updatable system for analyzing school competitiveness. TrueSKill helps us grasp the strength disparity between schools, while the LLM makes the data easier to understand and apply. In the future, we hope to incorporate more dimensional data, such as the school's academic performance, regional development, or student satisfaction, to make the model analysis more comprehensive. We also hope this system can provide educational institutions with more precise references for their admission strategies. Finally, we would like to extend our special thanks to Professor Chen Dezheng for his guidance and assistance, as well as to all team members for their hard work in data organization, model design, and system development. That concludes our capstone project presentation. Thank you.